Hey, Mr. Baldwin.
Hey, Miss Awad.
Guess what we're talking about today?
Bowling. No?
Mr. Baldwin, we are not talking about bowling.
Volcanoes.
We're talking about volcanoes.
Gotcha. Good.
Okay.
Alright, so we're talking about volcanoes today.
We are.
Good.
So what we're going to do is we're going to talk about a lot of things related to volcanoes, like why, when some volcanoes erupt, are the eruptions very different from other volcanoes?
Mm-hmm.
Why, in some cases, can scientists and even tourists almost walk up to where the volcano is erupting?
And like some of them are like super explosive, really deadly.
Yeah.
Yeah.
So what is it scientifically, geologically, that makes the volcanoes different?
Okay.
Okay? So the first thing we're going to talk about is the silica content in the magma. All right? So how does the silica content in the magma affect the type of eruption in a volcano?
Well, from what I remember from our mineralogy and Bowens and the silicate structures, when it was really high temperatures, there wasn't a lot of silica in the magma, right?
It wasn't as concentrated, right?
It wasn't as concentrated. So I'm thinking it's almost like if it's not as concentrated of a liquid, it probably changes how the flow works, right? And my guess is it flows really easily.
Yes, so
Okay.
it's not viscous.
Okay, yeah, it's a low viscosity fluid.
Right.
Now, we might have to define viscosity for some of these guys.
Okay, well, let's do that.
So viscosity simply is a liquid's resistance to flow. So something with a high viscosity would be like maple syrup.
Okay, and something with a low viscosity would be like water.
Yeah, absolutely.
All right, good. So what we're saying is that sometimes when volcanoes erupt, the lava is very high temperature, and because it's high temperature and it has a lower concentration or a lower amount of silica in it, it's going to be lower viscosity, so it will be more fluid.
And it's going to flow really easily.
Runnier and flow easily.
Okay.
So I think we have a video here that is taken in Kilauea in Hawaii, and there's several different parts in this video. So I think what we're going to do is we're going to play the video for you to show what happens when Kilauea, which is a basaltic volcano over a hot spot, right?
Mm-hmm.
What happens when that volcano erupts. And we're going to try to mute the sound on the video because it's a lot of wind noise, and we're going to try to talk over that video, right?
Cool. Field trip.
So here we go. Let's watch the video.
Sounds good.
All right. Okay, so at this point what we're seeing is we're seeing some of that very low viscosity lava. It's actually dripping over the side of the cliff, and in a minute they're going to show it splashing into the water.
And it's almost like flowing just really easily into the water, and it's got to be cooling really quick, right?
Yeah, so that lava is over 1,000 degrees C, and of course the water might be 75 or 80 degrees.
Yeah.
And when it hits the water, you see the steam coming off the water. There's a really interesting feature that happens there. We talked about quenching in class, right? So when it immediately freezes into a glass.
And there's no time for crystals to form.
Exactly.
Yeah.
There are something formed called hyalocrystites.
Hyalocrystites.
Yeah, and those are formed actually when the lava hits the water, and it just like shatters into a glass, but it shatters into a glass underwater. So they find little itty-bitty beads of this glass in the water. So it is very cool. And now we're getting into a little bit different scenario here. So we're looking up closer to the crater at some of the rivers of lava that are actually flowing from the crater down the slopes towards the shoreline.
And it almost looks like the lava's like splashing around and almost behaving like a liquid, like water we think of.
It does, yeah. So if you ever get a chance to go to Hawaii, one of the really popular tourist destinations are the lava tubes.
Mm-hmm.
How are these kinds of flows associated with lava tubes, Mr. Baldwin?
Well, I'm seeing that it kind of flows like a river, and my guess is at some point it's got to solidify just like a river would. Or not like a river would, but it would solidify in the shape of a river. So my guess is somewhere along the lines we could like go into one of those lava tubes if it got eroded away, right?
Right, so the lava tube itself, the pipe-like structure that you walk through when you go there, is made out of what that black shell is on the surface of the lava.
Oh, cool.
So that is the quenched lava.
Okay.
And then the lava has flowed through there, and when the eruption stops, there's no more lava flowing through, so it just leaves that black shell behind, and that's the lava tube.
It's like a big tunnel almost.
Yeah, it is like a big tunnel.
Cool.
So I think now at this part of it, we're starting to see a feature that's called a lava fountain. And lava fountains are very typical of Hawaiian eruptions, especially on Kilauea. So this lava is a basaltic lava in composition, and we already said it was very low viscosity and very high temperature and very low silica. So that allows it to form into these fountain-like eruption structures.
And if it's basaltic, once this cools, it's probably going to be really dark because it's mafic, right?
Correct.
High iron and high magnesium concentration. Okay, good.
Ferromagnesium silicates. Great. So here's a nice... Well, that was a really good video, Mr. Baldwin.
Yeah, it brought me to tears, absolutely.
I see that. What are we going to look at this time?
We're going to check out Mount St. Helens.
Okay.
And Mount St. Helens was a mountain, or a volcano that erupted in 1980 in Washington.
Yeah.
And it was andesitic composition, so that means it's intermediate, right?
Okay.
Okay.
Yeah.
And my guess it's going to be different viscosity. And there's going to be a little bit different. So if it's higher viscosity, it's probably going to be more resistant to flow.
Okay.
And if it's more resistant to flow, my guess is it can hold a lot of pressure then, right? Let's see what happens. I think this will be pretty cool.
All right, let's take a look at this, then we can come back and talk about it. All right, here we go.
So here's some pictures of Mount St. Helens. And these are just pictures. They didn't have great film of it.
Yeah.
And it was over a 57-second period.
Yeah.
And this was the eruption that we saw. I mean, this is what a lot of people think of when they see volcanoes.
Yeah.
These great big eruptions. So this is more or highly viscous, and it can be highly explosive.
So let's actually play that back. Let's actually go ahead and play this video again. But this time, let's ask the students to focus on the shape of the volcano right now. So kind of draw a picture in your mind's eye of what that nice cone looks like and the crater at the top. And then see if you can follow along where the eruption comes from. All right, let's take a look. So it's isolated on the right side of the volcano, right?
And it didn't totally blow off the top. It almost blew the side off of the volcano.
Yeah, so that was the north side of the mountain.
Okay.
And it actually blew about 1,000 feet of elevation off that. So let's talk for a second about the difference between Kilauea and St. Helens eruptions.
So we said Kilauea was low viscosity, low silica, and it really just flowed easily. It wasn't very resistant to flow.
Right.
And
Mount St. Helens is much cooler lava with a higher silica content and a significantly higher amount of gases. And that's why it's a more violent eruption.
okay.
But it's the silica content that's going to control part of that, because if we remember from Bowen's reaction series, when you get to the intermediate composition, that the silica content has increased.
And
right?
we're even making more complex structures too. We've got like bigger molecules that are present.
Yeah.
And those bigger molecules probably slow things down a little bit from flowing.
Right. Hey, and since we're here, let's just talk too about Kilauea is in Hawaii, and that's on a hot spot.
And Mount St. Helens, it's on the west coast of America.
Right.
So that was a convergent zone, wasn't it?
It's a convergent plate boundary.
Okay.
In part, but there's also the Juan de Fuca Spreading Center just offshore. So what we're seeing is that downgoing slab. It's a very young slab going underneath the northwestern corner of North America.
Okay.
So that's what's causing that volcano.
Okay.
So here we have a volcano in a convergent plate boundary with an intermediate composition. And I think that's something that when we start to look at the plate tectonic association with different types of compositions, that we're going to see a pattern like that.
Okay.
Okay? Cool. Let's go on to the next slide then. So we've talked a little bit already about viscosity. What are we going to focus on here?
It looks like we're showing the relationship between temperature and viscosity.
Okay.
And what I always think about when I think of temperature and viscosity is eating pancakes.
Okay.
And when I eat pancakes, I always put maple syrup on it. And it's always terrible taking maple syrup from the cabinet. Because like you sit there and it doesn't pour, it's like really slow to pour out. So you put it in the microwave.
Yeah, warm it up.
You warm it up, and when you warm it up, it flows really easily.
Okay.
Okay, so when it's colder, the viscosity is really high. And when it's warmer, viscosity is really low.
Okay, so we have another couple of video examples here. The first one. What is that noise, Mr. Baldwin?
Oh, it sounds terrible. It sounds like broken glass.
Okay, so this is lava flow that's very viscous, and this is forming a structure that's called, the type of lava is called a'a in Hawaiian, because if you step on it with bare feet, you will say a'a, not because it's hot, but it's so jagged. And it's jagged because it is clenched against glass, and it is just shattering as it forms, so we're hearing that glass shatter.
Oh, sounds awful. It's amazing how slow it moves too. Like you don't see much flow going on there. It's just really slow, creeping forward, creeping on, making lava really slow.
You can tell the cameraman was right up there filming that, right next to it. Not where you want to be in St. Helens.
No.
This one you can easily walk away from. So that was a good example of an flow forming, and now we have another Hawaiian term.
Okay.
This one is
a pahoehoe.
Pahoehoe. Good. Okay. So we're going to see another Hawaiian volcano here, an example of a pahoehoe flow. Okay. How is this different than the flow?
Well, this one's going to be low viscosity. So low viscosity means it's going to be highly fluid, high temperature. So I think it's going to be moving quicker and kind of flowing, almost looking like water.
Okay. So pahoehoe, I think, means ropey.
Ropey, perfect.
So let's take a look at this one.
Ready?
Yeah. Oh, they're right there watching it.
Right. So now this one is just moving. Like I said, ropey. It looks like it's a rope just kind of flowing pretty freely. It's not breaking any boundaries. It's just a big flow.
Very different.
Okay, so we saw the two different types of lava that we saw, the and the pahoehoe.
Right.
Okay, and now we're looking at lava formers. So we want to see the relationship between, again, temperature, silica, viscosity, and making lava, right? Okay.
Because as we know, when St. Helens erupted, we didn't see lava. We saw a huge pyroclastic cloud, which had the ash and the gases in it, and water vapor. And when we saw the Hawaiian ones, we saw lava. So there's something going on that's different between those two. And in this video clip, we have a nice story about a volcano in Mexico called Paracutan Volcano. And I think this is a great little historical episode about that volcano and the formation of it. So let's take a look.
Let's go for it.
All right.
La historia se comienza así. El volcán nació en el 1943. Día y noche estaba aventando lumbre, estaba aventando arena, estaba aventando lava. Y estuvo durante 9 años en erupción, 9 años. Yo nací en el 45, después de 2 años cuando nació el volcán. Si yo recuerdo un poco, como de sueños, me acuerdo un poco cómo se veía en la noche y todo. Este pueblo se llama Angawan, donde yo vivo, Angawan, Michoacán. Pertenecemos a Uruapan. Estamos oyendo nuestro dialecto purépecha. Aquí casi la mayoría no habla español. Puro purépecha. Está anunciando cosas, lo que venden en sus casas, como verduras, chiles, jalapeños. Ahí se anuncia, como por ejemplo en el radio. Antes del volcán, ahí era una tierra de cultivo. Ahí andaba un campesino arando con su yunta, que de repente se siente como que la tierra se abre, entonces empieza a salir humo. Entonces ese volcán no estaba, ese volcán nació en una parte de sembradío de maíz. Era muy triste para nosotros porque en aquel tiempo se acabó todo el cultivo, toda la tierra no servía nada porque la arena tapó toda la tierra fértil, entonces pura arenal, como un desierto, todo pura arenal, negra, todo se veía.
Subterranean inferno, burying a village of 600 people.
Y esa gente no murió porque el gobierno vino y lo sacó a toda la gente y lo cambió cerca de Europa. Entonces ese cerro se fue formando poco a poco. Duró como cerca de 2 años para que creciera a esa altura lo que ahorita estamos viendo. El volcán todavía pues nos dicen que va a volver, pero quién sabe si será cierto. Hey.
So that was a different volcano in terms of the style of the eruption. It only took a short period of time for that volcano to grow, and people were actually there to see it happen. And how, geologically, how was that different from what else we've seen here?
Well, it was really explosive,
Yeah.
but really small.
Right.
So, like before, we had really big and not as explosive, and really big but really explosive. Now we've got small and explosive.
Right.
So, I guess since it was explosive, it was probably pretty viscous, right?
Yes.
Okay. So it means it was a lot colder.
Mm-hmm.
It's weird to think of a volcano as cold, but
I know.
yeah. And since it was really small and short-lived, I mean, do you think it was something that was constantly feeding it, or kind of ran out of juice,
I
right?
think it kind of ran out of juice. So we saw a different kind of material being erupted from this one, a higher silica material, lower temperature, and more viscous. And that's the result of that kind of eruption. So we're going to talk in another episode, a couple segments from now, about how that volcano itself, the shape of it tells us that it's a different type of volcano. So we'll get on to that. But I think we have a little bit of a check for them on this segment.
Just a quick quiz. If you go back to your class site, there should be a real quick quiz based on the videos you saw, based on what we told you here.
Great. See you tomorrow in class.
See you guys.
Bye.